Okay, so the three topics that were most popular in the poll were invoking external components like perception or planning or control components from inside Scenic. We've already seen a little bit of that. I mentioned how you call arbitrary Scenic code, Python code from Scenic. So the kind of thing we have in mind in situations like that where you have some external thing. Oops. This is for later. We'll come back to that. So imagine you're writing some scenario where you have some external controller for one of the agents, for example. So we might say that the ego card is being controlled by some external software. Autonomous driving spec that I have outside. So there are a couple of ways you can deal with this. One is if the car or if the software stack that you're using is already interfaced to the simulator, you could basically just not create this object in Scenic and just let everything be managed by the existing software stack. That's okay if you have like a fixed starting position for the car or something like that. If you want Scenic to be able to position the car initially, then we would need some way to basically have this software that you the controller that's external know about this car, that this is the one it's supposed to drive. And different simulators have different ways of doing that. For example, in Weebots, I showed the example before where we had the Mars rover going through the field, and there inside Weebots we could select for each robot what external script it should run to control it. So that varies by simulator. One thing you can do, though, that is simulator agnostic, is route everything through Scenic. So have Scenic invoke the external planner, controller, and that sort of thing, and then pass the decisions that those make onto the simulator. That will work with any simulator that we have interface to. So it allows you to write things in a somewhat more simulate agnostic manner. And the way you do that is basically by writing a behavior which calls that external code. So we could do something like, there we're going to define the behavior, and you could do something like, let's say our external controller is in some other Python module, right? So this is like, I don't know. It's not actually like this, but let's say AutoWare had some Python interface, right? When we can import that, then you could say, all right, let's get the steering, throttle, or whatever other stuff. We'll this by something like this, right? So you can call some external Python function. You could pass into it any state that Scenic knows about. So maybe this external thing is going to look at the current position of the car, its velocity, maybe some other information, use that to decide what to do next. You can pass all of that through here and have it return whatever controls it would like to apply. So in this case, say steering and throttle. And then we can tell Scenic to send those to the simulator. So we saw that before. It's like set throttle action, open backwards. Something like this, right? So if we write the behavior this way, then the software that we're calling doesn't actually have to know anything about the simulator. It can just talk with Scenic. So the advantage of this is that we don't have to worry about issues of synchronization, like if the software is running externally, if Scenic wants to pause the simulation and now start a new one where the car gets teleported somewhere else, for example, this might confuse the software stack, and it now suddenly looks like the system is in a totally different state than it previously was. With this way, you have full control. So we could even do things like if there's some initialization that needs to happen at the beginning of the simulation, once the car has been positioned, we can do that here. So we can call that a function. So if you write it this way, you have total control. You can start things up here. You can let the system know, all right, we're ready to start a new simulation. You can tell it when it's time to compute a new thing, new controls, all that sort of thing. The main downside of doing it this way, well, two main downsides. One, you have to write this kind of linkage code here. And it may be that for some simulators like Carla, they may already have an integration to some software stacks, which you wouldn't be able to take advantage of as easily this way. So that is one downside, but it's what you get for basically having the flexibility of controlling everything from Scenic. The other potential downside here is that the time step you're using becomes pretty important, right? Because here it may be that, for example, the steering and throttle or whatever the controls your system has may need to be set very frequently. And if all the communication is going through Scenic, like here, this means you'll have to use a pretty small time step in Scenic. So that could introduce some overhead in the simulation. But this is probably the most robust way to write things, where you are invoking everything from Scenic. So then Scenic has control of when should the simulator run, when should the external software stack run, etc. So it's just to illustrate that you can call kind of arbitrary external Python code from Scenic. And if you have software that's not written in Python, there's also various foreign function libraries you can use to invoke those through Scenic if you want. You can also use other mechanisms like socket networking, things like that. That's actually how some of our simulator interfaces work, like the Carla one, for example, communicates to Carla with the network stuff. So that's, I think, basically the idea on how you could invoke external components from Scenic. There's no secret, really. You just treat them like functions. You can call them inside behaviors like this, and everything will just work. I should mention that it's important here that everything is being called inside behaviors. If we try to do something outside of this, like suppose we did something like this, maybe we tried to do something like this, right? This looks like this might work, right? You're saying, well, I've already figured out where this car is, so now let's set up this software. But as we talked about in the previous session, this ego position is actually not going to be concrete value. It's going to be one of those distribution objects representing some distribution. So you're going to get some error from this external function, which is like, I expected a vector, and you gave me this weird distribution object, right? So if you call stuff from the top level in Scenic here, sampling hasn't happened yet. That's not going to work. So that's why this sort of thing should be put inside a behavior, by which time you have concrete values ready. Scenic also has hooks. If you need to do it even earlier than this, like as soon as an object is instantiated, but before you've started to run the behaviors, there are also hooks where you can put in code that way. If you look at the object class, there's documentation on that. But anyway, just a little warning there. If you are calling external code from Scenic, if you do it at the top level when things have not yet been sampled, your code will have to deal with Scenic distribution objects, which is probably not what you expect. So if you want things to be called afterward, like once things have been sampled, it either has to go inside a behavior, or if you want to write a helper function that like takes a random value and does some transformation on it, there's also a decorator you can use for that, which is a somewhat more advanced thing. So I'm not going to talk about it here, but I'll just mention if you want to look that up. This is also discussed in the documentation. If you go to like the syntax guide, where we have our built-in functions built into Scenic, these functions are all designed to work with distributions because those are like first-class Scenic objects. But if you want to call some other Python function that's not listed here, you can go under like miscellaneous Python functions here. And you'll see there's this note being saying here that if you want to pass random values into some other external function that doesn't know about distributions, we have a decorator you can put on your function for that. And what this decorator basically does is it defers the evaluation of the function until sampling. So if you define some function f, say f of x, and x, it's expecting x to be a number, then if you put this distribution on this decorator on your function, Scenic will ensure that if a random value gets passed in, we'll wait to call this function until a concrete value has been sent. So just want to mention that so you know that exists in case you need to be writing helper functions that might take in random values in pure Python. This is something to help make that easy.
So if you want to, let's say for something like AutoWare, I'm making this up, but you want to call a function in the initial state,
right?
But it's dependent on the sampling of the object and other objects,
right?
What's the best way to do that? Do you create a dummy object and kind of define a behavior?
I would do it in a behavior, yeah, right. So exactly. So I would make a thing an object which is supposed to be the card controlled by AutoWare, and then do that initialization at the.
I mean, I said AutoWare, but let's say
whatever it is. Yeah.
It's like there is some kind of a system that is taking in estimates of the position or the positions of all of these things, and then computing some function of that at the initial and publishing that information, right? So it's not like any given agent, but it's just another object.
Okay.
So you just define, or it's just some other initial. It's some state, a global state that all agents share.
Right. If it's global state like that, then I would recommend using a monitor for that. So we actually, I don't think we touched upon this in any detail before, but Scenic also has a concept called monitor. So this is basically like a behavior in that it runs in parallel with the simulation, but it's not associated with any given object. It's just something that runs on its own. So here you could do things like call your initialization thing there, and then you can do, if you wanted to do stuff during the simulation, you can do things like this. And then to actually cause this monitor to run, the syntax is like this.
But can the state of the monitor influence the state of others?
It can. So you can in here like mutate things. So you could say like, my global flag equals true at some point.
And then other agents
could read that. Yep, if you have that set up here. So
that's we can talk about this offline, but we always got to monitor the specifications, right? And so
So this is
in general, you don't want the behavior of your agents in your model to depend on specification variables.
Right? Right. So this will be using a monitor for a different purpose than providing a specification. You can put it inside a behavior.
Here's a concrete scenario where imagine that there's some number of objects that are spawned in the environment, cars, drones, whatever, and then there are just sort of maybe top-down images of all of these things that are being sent to some kind of central state estimator, right? And so once you sample the positions, etc., you render that initial scene, and that initial scene is then sent to this thing, which will then compute the state estimate and publish it to everybody.
Okay.
And this is one of the initial condition thing.
Right.
So it seems like one way you can do this is you define an object for that and a behavior, and then that behavior has to run in the initial state. Right?
Yeah, and that would work. If you just have like the first object be this dummy object, right? And you can set some flags on it so that Scenic won't care about it intersecting with other things. It's a super fake object. And then its behavior will run first. So you could do it that way, just to make a dummy object. Okay. So that a takeaway from this basically is just that you can call external Python code and use that as part of behaviors to invoke external modules of some kind. Okay, so that's that. Now, one thing I wanted to show, and then give you a chance to play around with, is the concept of external samplers. So I've mentioned a couple of times now. I've mentioned a couple of times now that Scenic allows you to define external parameters. So these are parameters that don't have a fixed probability distribution on them, but which some external tool like an optimizer can assign. So the documentation for these is under this part of the internals. So you've got external support the values which are sampled outside of Scenic. So I won't go through the details here, which is basically explaining how these work. But how you can think about these are basically like holes in the Scenic program. So somewhere where a number should go, you're putting a hole saying, I'm not saying what value this should be. We're going to call this external tool to put in a number. So you can think of it as the Scenic program taking inputs is another way of doing it. There are parameters which are inputs to the Scenic program. Once you fix these parameters, then the distribution for everything is defined. So the way that the main way that people have used these so far is using VerifAI, our associated tool, which Sanjay talked about, as the source of the values for these external parameters. So you can actually use this to hook in all kinds of external tools. But the one that we have built-in support for already is for using the samplers provided by this VerifAI toolkit. So in particular, there are constructs like VerifAI range and VerifAI options, which mirror the normal distributions like range and options that we have in Scenic. So let me just show you that example that I was making here. So here I've defined a scenario with one global parameter I'm calling x. And I'm saying instead of it just being a range like this would mean x is a uniform random number between 0 and 1. If I run this, here I'm going to run using this show params argument so we can see the value of these global parameters. So I don't actually need to render anything to this function. Okay, so you can see we got some value for x. If I sample another scene, you get different values for x, right? Between 0 and 1. These are random values. Okay, fine. Now, if I want to use some external tool, I can use other kinds of parameters. In particular, to use the samplers from VerifAI, I can replace this with a verified range, which basically means a value in the range 0 to 1, which is chosen by VerifAI. And the default configuration for VerifAI is to use one of VerifAI's samplers called the Halton sampler. Oops. No, right. So it's the slider. Yeah. So Halton sampling is a low discrepancy sampling technique, which basically tries to give an even spread over the space of possible values. So if you may have seen pictures of this where if you sample random points within a unit square, for example, there tend to be clusters. If you just sample completely at random, some places tend to get higher density and some less density just by chance. It doesn't deliberately, try to cover the space even. Right? On average, of course, it does cover it, but it's not very systematic, and so you end up with gaps and holes and things. And low discrepancy sampling is a way to more systematically cover the space so that there aren't gaps. So this is a sampling technique that's good, for example, when you want to kind of exhaustively cover a range of parameters and find which regions of the space work better than others. If you want to just cover the space evenly, you could use low discrepancy sampling. That's what the default configuration for VerifAI is when we use it. We've seen it like this. So you'll see if I run this program now, the first value I'm going to get is exactly 1/2. And if we iterate on that, then I'm going to get 1/4, then 3/4, then 1/8, then 5/8, etc. You see, it's actually like systematically going through the interval between 0 and 1. And if you did this a lot, you'll see it's actually unique every time. It's also deterministic, this particular sample. So if I can quit this and do it again, we'll get the same sequence. 1/2, 1/4, 3/4. So this kind of thing can be helpful if you're trying to just systematically explore a range of parameters and see which places are good and which are bad. So actually in the example that Sanjay showed earlier with the taxinet scenario on the runway, we used Halton sampling for the initial falsification there because we wanted to evenly cover the possible times of day, positions on the runway, etc. Question? Did you have a question? Oh, I had one thing. Sorry. Yeah.
In the diagram that Sandra showed, it seemed very irregular. This seems very irregular. Was there a reason?
Which line?
Because it was projected, so there was a 3D space projected to 2D.
Okay.
So you were seeing the effect of that.
But did we actually show the?
And it was also,
I think this was he to show the graph
I
at
showed-
time of day, right?
no. He's talking about TaxiNet.
Yeah.
What I showed was for the AAA
Yeah.
study, and that too was projected down one lower dimension.
Okay.
Yeah. Okay, so this is an example of one kind of sampler you can use from VerifAI. But flipping this around, suppose you don't want to evenly cover things. Suppose you want to try to intelligently go towards places where the system behaves badly. VerifAI also has samplers that do that. So in particular, there are optimization techniques like cross-entropy optimization, which will try to drill down and find the parts of the space where something bad happens and investigate those parts of the space in more detail. So you can control that by telling VerifAI to use a different sampler here. And that's documented over here. There's some global parameters you can set, particularly this VerifAI sampler type parameter here. I'm saying use cross-entropy sampling. That's what the CE stands for. So in fact, in VerifAI, we have quite a few different sampling and optimization techniques, which we won't go into here. You can check the VerifAI documentation for those. I'll just show you where that is. I think is it linked to from here? I think it might be. Oh yes, there it is. So we have our other repository for VerifAI, and in the README there we link to our documentation, and that's got a list of all the samplers and search techniques. So you can sample from a Scenic scenario. That's actually what we're doing kind of implicitly here. But then, oops, where is the? This isn't actually the list of them then. Okay. Oh, I guess we're mentioning some of them here. But the details of them must be somewhere else. I want that. We have several different techniques you can use. All of these are exposed in Scenic using this parameters like this, VerifAI range, and so forth. You can basically specify that all of these parameters are controlled through one of VerifAI's.
I think it's probably the feature API.
Maybe that's what it is. Okay. So I won't go into too much detail here, but I'll give you a chance to play around with this in a second. If you want to try putting some of the, if you install VerifAI, you could install VerifAI, and then it might actually be already installed if you've done the dev install of Scenic, because it's an optional dependency of Scenic. You can add in some of these parameters and see what kinds of effects you can get there. One of the things I'll mention that's in here, just a cool thing that we won't have time to get into, but just want to show you how you can do it. One nice way you can combine what Scenic can do in terms of probabilities and what VerifAI can do with optimization is using Scenic's distributions as prior distributions to initialize sampling. So in particular, the cross-entropy sampler that VerifAI has allows you to give prior distributions from Scenic. So here what I'm doing is I'm saying, let's create an object where the x-coordinate, if it was just Scenic, it would be a normal distribution with mean 10 and standard deviation 3. That would be a fixed distribution. But now we're saying use VerifAI's cross-entropy sampler to actually find to start from that distribution and try to push that distribution to converge on failure scenarios, cases where the specification of the system is violated. So you're saying this is the prior distribution, this normal distribution, and now VerifAI will start sampling from that distribution, but based on the data that it's getting, start moving more into putting more emphasis on the parts of the space where crashes occur or whatever system level failures occur. So in order to do that, you have to actually tell VerifAI what the specification of your system is so that you can then try to violate it. And that's explained in the VerifAI documentation. So there's an example. If you'd like to play around with it either now or in the next session, you're welcome to try running some of these examples from the VerifAI repo. There are some that use Scenic built in, like the this emergency braking one. And where's the oh, sorry, yeah. In the basic usage part, we describe how you can write a specification. So here is, for example, like a simple specification written in retrotemporal logic. So VerifAI has various ways you can use to specify what condition you want to monitor over the system, and then try to falsify. So which basically give a goal to verify search techniques, which is to try to make that condition false. Okay, so I think I'll stop here now and let you play around with this for a little while, for the next 15 minutes or so. If you want to try playing around with these external parameters or running any of the VerifAI examples, I'll put back up here the basic syntax. Right. So I'll show another example here just in the interest of time, just to illustrate what's going on here a little more. So here I've written a little Python program using Scenic's API. Here's a similar scenario to the one we had there. So we've got X is VerifAI range between -1 and 1. What I'm going to do here is I'm going to generate scenes in a loop like we saw yesterday. The part that's new is I'm using this feedback argument here to basically pass feedback to the external tool saying, what was the outcome of this sample? So here I'm saying sample a scene, get the value of the global parameter X. If the value is positive, let's say this was good, this satisfied our specification. Let's have our result be 1. Otherwise, it'll be -1. Okay, so this is like simulating. Imagine that instead of just checking the value of X, we now like ran some simulation or something. And if X was positive, the simulation succeeded. And if X was negative, the system did something bad, right? So then I pick that as the result. I pass it in as the feedback. If I didn't use VerifAI range here, if I just use the range, let's do this. Then when I run this, oops, you see I'm getting, equal numbers of negative and positive values for X because it's a uniform distribution between -1 and 1. But if I put this to VerifAI range, and I'm using cross entropy here, we'll see this will converge to the negative numbers where the thing was violated. So here I ran 100. You see, by the time we get towards the end of these 100 rounds, we're only generating negative numbers. So if we look at the beginning, up at the start, the cross entropy sampler has basically an even mix of positive and negative ones. But it's getting these feedback. It discovers, oh, there are more failures on the negative side. And yeah, you see by round 30 or something, it's converged and it's now only generating negative values. So this is obviously a toy example, but this is the kind of optimization you can do with these external tools to try to zero in on the parts of the space where something interesting happens. Good question.
Why does it go to the negative values instead of the positive?
So the convention that we have here from VerifAI's optimizer is it's trying to minimize the cost function that you're given. So if you remember the example Sanjit showed, where the specification was to track the center line sufficiently closely, the way we constructed the cost function was such that if it was positive, that spec was satisfied. If it was 0, it's like just on the edge of being violated. And then the more negative it is, the more you violate the spec. So that's the same convention that we're using here. So here I said, if X is greater than 0, let's give positive feedback. If X is greater than negative, less than 0, give -1 as the feedback. And so since the optimizer is trying to make it as negative as possible, it's concentrating on the cases where X is not greater, so that this feedback would be -1. Does that make sense?
So X would be negative.
X would be negative, right.
Or not greater than 0.
Right, but I could make, for example, let's say maybe you only get positive feedback, or if it's like, it has to be at least -1/2, right? Then it should converge to between -1 and -1/2, because that's the only region where you get the -1. So let's try it. There you go. You see, towards the end here, we're only getting things that are more negative than negative plus.